Okay, now we have to insert okay, let's run the program. Okay, nothing because we didn't insert the function. Okay, for servo we need 1 divided, yeah, correct. Okay, and for the aircraft we need to insert 0.1 here and 2 here. Okay, till now everything's fine. For 0.1 and what, and 1, I think. Yeah, s power 2 of 1 plus 4 1. Okay, yeah, everything is fine. And yeah, we can also, let's I shouldn't have changed the color, right? Okay, I made a change here, sorry. I undo it. I actually I press down Ctrl Z and try to undo it. I think 1 here. Okay, right. Okay, I want just to line width so we can see our graph better. Line width. Okay, that's fine. Okay, then I think we did everything right, because actually our response here matches what it should be, actually matches this graph here. Okay, but we need a compensator. For the compensator, I told you that we have to use mass script, but I do not want to go step by step and make the second program. I show you just the solution because you have just to type the commands in your mass script node and everything will be fine. I already made that program. I have to just find it. Yeah, here. Yeah, this is the correct code. Actually complete, no, not still not complete. Yeah, this is the complete code. You have to enter in your mass script node. We already worked with mass script node, and you should be familiar with the commands used in with the commands used in this node, and also how to use this VI. You see, first we made our transfer function of our compensator controller, as shown here. At the end, we use TF, which makes our transfer function. This is numerator and this is denominator. We use these two to make our GC, which is our transfer function. Then the transfer function of hydraulic servo, just like before, aircraft, and actually we put all these three in a series in this way. G is equal GC times G1 times G2. Actually this way we put these three transfer functions in series. And also we make the closed loop system with a unit feedback like this. CS is equal feedback G, which is the in fact multiplication of these is the result of these three functions, comma 1. Actually what we have here, CS, is this closed loop system, and G is the upper part. Actually yeah, is GCS times 1 divided by S and times this transfer function. Okay, alright, and the rest is clear. Just a step response of CS, equations of hydraulic servo and aircraft, the root Lucas graph of G. Again, as you see here, we use the open loop transfer function to draw the root Lucas graph. And also this also just shows the compensator controller equation, the transfer function of the compensator. If I run it, yeah, you see everything is fine, and the response here, first of all, the problem was solved. Don't have those high amplitude oscillations at the beginning. The settling time was reduced, and this is our root Lucas graph. Again, you can I'd like to have them a little bigger. Okay, the rest also you can actually, you just need to, okay, it's running, and you just need to drag this box here, and other plots also appear. Other plots, I mean these, actually I mean these curves. For example, plot 7, and it's this blue line here, blue curve here. Okay. Yeah, that's it. We are done with our program, and I show you what the response should be. Yeah, you see, if I put it here, you see anyway. Actually, the response here is a little different. I don't know why. Maybe we did something wrong. Let me see the hydraulic servo. But in fact, yeah, the root Lucas graph is pretty the same. The picture is just a little bit somehow pressed, but more or less is the same. As you can see, around -6 we have, yeah, it goes to, yeah, exactly. Yeah, -2. Yeah, actually root Lucas graph is pretty the same, but the unit step response of compensated system is a little different. Let's see. When it's totally different. Okay, why, I don't know. Maybe compensator, we made a mistake in compensator. the compensator. No, it looks very the same. I'll just make a pause to see what could be the reason, then I come back to. Okay, sorry for the mistake. I found a problem. You see, this is the compensator. Actually, the equation or compensator we made. But if we go to our example, our problem, actually the suggested compensator controller actually has a factor here, as a factor of 88 point some. We didn't put this factor, this number here. Instead of putting the number here, I put the number here because it doesn't make any difference. Like gain factor, it's like having a gain factor in series with our compensator. It doesn't make any difference. I put my compensator here, 88. Yeah, and run it. Yeah, you see, everything is very the same. Exactly. Okay. There is one point to learn from this mistake. As you saw, when we inserted the factorial, actually that's 88 point something. They inserted that number. There was no change in our root locus. This is the point here. The gain factor doesn't change the shape of our root locus. Okay, I hope this video was helpful for you, and I thank you for watching.